I'm Sumanth Prabhu. I'm from Data Consultancy Research, Pune, India. I'll be presenting our work on efficiently learning safety proofs from appearance as well as behaviors. So this is a joint work with Kumar Madhukar and R. Venkatesh. I'll begin with the problem, and the problem is to learn safety proofs. And we all know for correctness of a program, we need safety proofs. And I don't think I need to motivate here why correctness of a program is important. So let us look at what are safety proofs. So we'll consider this simple but popular program. In this case, we will assume programs are, the variables in the programs are of integer sort. And so in this program, there's a non-deterministic while loop with both x and y being program variables getting incremented. X is getting incremented by 1 and y is getting incremented by x. So the property that we are checking here is whether y after non-deterministic loop iteration, whether y will always be greater than 0. So if one reasons out, then they can see that since x is greater than 0 and y is getting incremented by x itself, so y will always be greater than 0. That is one way of reasoning. Or second one is y is at least equal to x, and x is always greater than or 0. So these facts are represented as predicates here. X is greater than 0 and y is greater than or equal to 0, or x is greater than 0 and y minus x greater than 0. So we call this safe inductive invariants. We saw in today's morning talk about inductive invariants. But just in case, I'll again give a concrete example for inductive invariants. So in this case, these two predicates include initial states, which is x and y initialized, as well as it is closed under this transition relation, and also it is disjoint with the property. More formally, say we are given a set of variables and a primed version of those variables represented as v and v prime, and a set of formulas in, let's say we fix a first order theory, and those formulas represent initial state, transition relation, and set of states which we don't want to reach, called bad here. So in this case, given a candidate invariant, we need to check 3 conditions, as we saw in the morning as well. So first is initiation, whether initial state is part of the invariant, and then second is consecution, where we check whether candidate invariant is closed under the transition relation. And the third is whether the invariant is disjoint with the set of bad state. Or more concretely, we can look at previous example itself. So x and y was getting initialized to 0, so that being init. And the transition relation was x getting incremented by 1 and y getting incremented by x. And then the property was negation of the assertion. So these can be substituted here, and we can check the validity of these 3 checks. Now in this setting, we are interested in problem whether we can synthesize an invariant, and how do we synthesize an invariant in this case. There are numerous techniques, as you all may know. We are looking at whether we can get these invariants from appearance as well as behaviors. Let us look at what do we mean by appearance as well as behavior. So I'll start with appearance. We work in a guess and check framework. So in yesterday's talk, we saw a guess and check framework in a different setting. And in this case, say we have 2 modules, learner and an SMT solver. So learner proposes candidate invariant and asks for certain tests. So tests being here init, consecution, and safety. And then an SMT solver can, if it is possible to decide, will decide whether the tests are successful or whether it failed. And if it failed, then it will return a model, which we call examples here. So in this setting, we call learning as iterative learning. That means, say a learner proposes candidate invariant, and it passes init and consecution. but it fails safety, but we still consider such inductive invariants, and then we try to get a more stronger inductive invariants from there onwards. So we call these individual candidates as lemmas, and in the end, we are trying to look at invariants which are conjunction of such lemmas. In this setting, we look at learner module. Suppose, say, we'll go back to the previous program. Say we have a set of formulas which is there in the right-hand side, and some kind of ranking among those formulas. Let's say probability of choosing that formulas. So in this case, if you go back to the first safe inductive invariant, which was x is greater than y as well as y is greater than 0, or x is greater than 0 or y minus x greater than 0. So if you see these set of candidates, we have a 0.4 multiplied by 0.3 plus 0.1. So 0.12 probability of choosing a correct inductive invariant. So now the problem is, how do we get these candidate formulas? And second is, how do we rank among those candidate formulas? One of the work by Fedorkovich and colleagues is to get these candidate formulas from the program itself. So the basic idea here is one can get these candidates from the syntax of the source code. We will briefly look at how it is done. Going back to the previous program, let's say the first statement, the initialized statement, as well as the property is normalized to a particular structure. So this being inequalities, let's say the equality was x is greater than 0 and minus x is greater than 0, and then y similarly for y, and the negation of the property, which is minus y and minus y is greater than 0. From this normalized formulas, we can construct a grammar which is particular to this program. So how do we construct a grammar? So let's say we do a top-down construction. We start with a candidate which is a disjunction of inequalities. Each inequality is a linear combination, and each linear combination will be a linear combination over constants, and again compared with another constant. So these constants and variables that are present in linear combination, one can get this from the program itself. So for example here, x and y are program variables, so variables will be x, y, and the constants for coefficients and the constant of the inequality, so this being 0 and 0, 1, minus 1, so for example from here. So this grammar will give a set of candidate formulas. So now how does one rank among those candidate formula? So in the same work, what is proposed is one can use frequency of different operators. So one starts with the top down, then one can use frequency of different operators in the syntax itself, and then can get a candidate formula. So for example, say how often does an operator which is greater than or equal to appear among inequalities? So for example, what is the probability that greater than appears in this normalized form? And greater than, there is only 1 among 5, so 1 by 5. So this particular approach worked well when compared to other state-of-the-art in 2017. However, one can see straightforward downsides. First thing being that there's an equal treatment for syntactic expression. Other than the frequency that they can get from the syntax, there's an equal treatment for all syntactic expressions. So can we use semantics here to get to find out which candidates are kind of have semantic value? Second is inability to get an appropriate order of sampling and checking. Say, for example, in previous cases itself, if one had sampled y greater than 0, then x greater than 0 and y greater than 0 would not have been, so y greater than 0 would have failed in consecution, and one would have been got x greater than 0 and y greater than 0 immediately. So this particular problem has been addressed to some extent in this Taka's paper by Fedokovich and colleagues, where they use interpolants to get some semantic value, and then they do a batch-wise consecution checking. However, what we see is we can get better semantic candidates, and we'll see a motivating example coming next. So our approach is, yes, so one can get from appearance, but one can combine this appearance with behaviors also. By behaviors, we mean the facts that we can get from semantics. So our contribution is to combine appearance as well as behavior, and then this may not work always. So we propose a heuristic which kind of gets conditional invariants. So we'll look at these two in the rest of the slide. Consider this program. So this is computing sum of first n natural numbers. Now the safe inductive, so one can see that the assert is, this program is safe because this being arithmetic fact, the 2 times sum is equal to n into n plus 1. So a safe inductive invariant for this program is this particular predicate. However, if you look at syntax in this code, so the second degree monomial for I square is missing in this syntax. One can add a mutation of this, but then again, it is not clear what kind of mutation needs to be added to the grammar. So we'll look at how can one get these invariants, and so suppose, say, we assume a candidate inductive invariant is of the form of a polynomial where we have monomials, some n monomials up to a certain degree over program variables. In this case, we want an efficient as well as one which can give us better candidates. So for this, we use the following theorem from Sharma and colleagues. So I'll explain what this theorem states with an example. Probably that is better. So consider a set of reachable states of the loop. So let's say we have unwound the loop, previous loop, and then we have got the reachable states here. These states correspond to the valuation of sum and I only. And now these states can be used, and let's say our candidate inductive invariant is of the form this, that is over all monomials up to degree 2 for program variables sum and I. Now the problem reduces to how can one find these coefficients A to F such that those inductive invariants have high chance to be, those candidate inductive invariants have high chances to be inductive. So the previous theorem states that one can use these states to get inductive invariants. So how does, so let's say we construct a matrix of the previous case. So we consider all monomials up to degree 2, and then use the concrete values of values that we computed at each loop head. Let's say 0, 1, and such values. Then this is up to degree 2, so we get sum square, sum times I, and I square. With this being the case, now one can get a linear equation over A to F, and then the previous theorem states that a null space of, so the matrix being the matrix that we constructed using states, loop head states, the basis of the null space of this matrix has, under certain condition, in fact, is an inductive invariant. But we ignore that condition, and then we look at the basis of null space of such matrix. So for example, here the basis being this case, which when substituted back to the form that we saw, reduces to 2 times this sum to I minus 1. Now going back to the program, so you can see that there is one more piece that is missing in the safe inductive invariant, which being I lesser than or equal to n plus 1. So how does one get this? So here we fall back to the syntax. So we are combining behavior as well as syntax here. So one can see that I lesser than or equal to n plus 1 can be obtained because the constant 1 is present here, and then I lesser than n is also present in this syntax. So now these two combination can give us a safe inductive invariant. However, this does not work always. So for example, consider this program. So what's happening here is there are two kind of phases where up to certain condition, the first part of the basic block executes, and then the second block of the basic block executes. Now if we unroll this loop to some finite way, then finite unrolling, then we may not get all behaviors, we may not get all reachable states, because it may always be the case that only this block is executed. So in that case, how does one get conditional invariant? So let us look at what is the invariant for this program. So this program has a disjunctive invariant, which is x is greater than or equal to large, and then y whenever y is equal to, and y is equal to x, and then x is less than or equal to 2 times large. So now what we propose is, instead of when we find such cases, what we propose is to get a conditional invariant. So by conditional invariant, we mean, say we fix the shape of the invariant of the form some alpha implies beta, and then we try to get alpha and beta. So for example, in this case, we'll propose this invariant, this as a candidate invariant, which is safe. So x is lesser than large, then y is large, and then x is greater than or equal to large, then y is equal to x. So now the question is, how does one get conditional invariants? So for this, what we propose is we can get antecedents from the conditions itself. So instead of considering entire code, we can consider only the conditions so that the search space reduces, and then the consequence we can get from the combination of behavior as well as syntax. That is one thing. But then how does one determine whether one needs conditional invariants or not? So what we propose is an heuristic which states that where we use CTIs. So CTIs, counterexample to induction, we define CTIs as those models which fail to get closure of transition system. So more formally, let's say we get a state which satisfies the invariant and also is closed under transition relation, but the next state is not part of invariant. So we use these pair of states to determine when to get conditional invariants. So to illustrate this, so let's say we assume a transition relation to have a polynomial relation. By that we mean, let's say all the next state variables can be represented by this form. That is, it's some polynomial over V. Now, if this is the case, then let's say we get these values from the CTIs, and then we check whether there is a solution over C1 to Cn, and whether the next state variables can be represented as a polynomial relation. So for this, we use CTIs and linear algebra. So let's look at a concrete example. So going back to the previous program, so we have a y, let's say y was large, and then a state large, and then we get large is equal to 100, and then x was also equal to 100, and y was also equal to 100. Next, what happened was we have got these two as conditional. We have got these two as CTIs, and then large prime being same, and then x prime got incremented by 1, and y also got incremented by 1. So this particular block has been executed. So in this case, we can see that the rank of we can use these values over all the variables, and then we can check that whether there is a solution or not. So from linear algebra, we can see that if there is a solution, then rank will be equal between the matrix that we compute using coefficients. So coefficient being here variables. So in this case, rank of these two were not equal. So in this case, we fall back to conditional invariants. Now, so to evaluate our approach, so we implemented our approach in a tool called Algebraic, which stands for our title, which is an extension of FreeCon2. So FreeCon2 being the latest, was the latest at that time. And then we take constraint horn clauses as input, and then we use Z3 as SMT solver. And the benchmarks that we used were from FreeCon2 itself, which were single loop programs over linear integer arithmetic. Now, so we wanted to check two particular questions. So first being, does this approach improve the capability of appearance-guided approach? So that by capability, we mean that does it increase the number of benchmarks that it solved? And second is, does the average time that it takes for a benchmark, is it lesser than the appearance-guided approach? Second being, does it hamper, that is, does it cause any regression in the existing tool? Because we get a particular shape, and which being heuristic, so does it cause any regression in the tool? So in experiment, we saw that in 24 programs which FreeCon was not able to solve, we were able to solve around 16 programs. So 12 of them being because of behaviors, and 4 being because of implications. Then also we saw 2 times speed up and around 100-second time difference for around 31 programs. Also, this gives a scatter plot. So the y-axis being the time taken by FreeCon in seconds, and then the x-axis being time taken by Algebraic. That is our tool. And this one can read more the number of points above this y equals x line, then the FreeCon2 has taken more time. So one can see here that FreeCon2 has taken more time when compared to our tool. And second one being, we ran our tool also with interpolant. So during that time, so we saw that few of the cases where interpolants used to give some candidates which were used here as well. So you can see here this getting shifted. Now to conclude, we propose an approach where we combine syntax as well as behaviors to find out, to get an interpretation for inductive invariants. Second being a heuristic to get conditional invariants when this being disjunction. Now, as future work, so we wanted to extend it to multiple loops. So this has been done, and this is to appear in FMCAT this year. Second being guidance from safety checks. So we saw that CTIs were used to get implication, but can we use the safety check? So if say safety check fails, can we use that also to get some guidance? Third being, the sampling is currently done using the frequency base. So can we learn a syntax of the program and then use that to construct the probability distribution? So those three are the And there are other future advancements which one can refer in paper as well. So thank you for your patience, and I'm open to questions.
So any questions? Questions?
So just this point about safety check counterexamples. Can you explain what you mean by counterexamples? True counterexamples or spurious counterexamples?
Yes, so if say safety check, yes, so there are 3 tests that a learner sends, so init, consecution, and safety. So let's say safety check fails, what the example that it gives, the solver gives, can we use that, can we generalize that as well? That is what we mean by counterexample here.
Any other questions? I have a question. Can you say something more about the implementation, your own implementation? I mean, which technology do you use, for example, to validate, invalidate the candidates?
Okay, so we use Z3 SMT solver as to check the 3 checks that we saw. And then this is developed over Freecon 2, so we use Freecon 2's.
Another thing, can you go back to the experimental data, so the diagrams you showed?
Yes.
So it's not very clear to me whether what is the impact of interpolants. You see, I mean, the 2 graphs are quite similar. So can you give us an idea of?
Yes, yes. So we don't accept some small cases here. Other than that, we don't see any much impact using interpolants.
Okay. Thank you. I suspected this, but I wanted to make.
Yes,
okay.
Yes, that is.
Any other questions?
Do you have some thoughts on also finding quantified invariants with appearance and behaviors?
Currently, we are looking at arrays where we try to get quantified invariants as well. So we are looking at some existing work on arrays, whether that can, for them, whether syntax or behavior can help in those existing work, which is from our group. So.
More questions? Okay, let's thank the speaker again.